Welcome to this specialized mathematics lecture on circles, designed for Class 10 students. The circle is one of the most perfect, beautiful, and ubiquitous geometric shapes in our universe. From the spin of planetary orbits and the engineering of wheels, to the teeth of gears and the cycles of clockwork, circular shapes drive classical and modern mechanical design. In structural dynamics, circular profiles distribute forces uniformly without pressure points, making them vital for pipes, arches, and structural domes. Today, we step into the mathematics of circles to master tangents, secant cuts, and contact points. We will prove the rigorous theorems of tangent perpendicularity and external side equality, unlocking the geometric secrets that allow physicists, aerospace engineers, and mechanical designers to build the rotary mechanisms powering our modern world. Let us establish the exact geometric definitions of lines intersecting a circle, which form the basis of circular calculus. Imagine a straight line and a circle on a flat plane. The line can relate to the circle in three distinct ways. It can remain completely outside, sharing 0 points. It can cross through the circle, cutting it at exactly 2 distinct points. This is called a secant line. Or, in the most interesting case, it can touch the circle at exactly 1 single point. This unique boundary line is called a tangent to the circle. The single point where they touch is called the point of contact. Tracing the coordinate grid, observe the secant line slicing through the circle in red, compared to the tangent line touching at exactly 1 point in green. This tangent boundary is the foundation of differential calculus and coordinate curves. We now introduce the first core theorem of Unit 4 circles, Theorem 10.1. The theorem states, the tangent at any point of a circle is perfectly perpendicular to the radius through the point of contact. This is an elegant and powerful geometric property. It means that the radius drawn to the point of contact locks the tangent line in a rigid, right-angled state. No matter how the tangent line tilts or rotates, the angle between the contact radius and the tangent line is always exactly 90 degrees. Tracing the radius segment OP in blue and the tangent line XY in green, notice the absolute perpendicular alignment. This theorem gives mechanical engineers and physicists a constant coordinate constraint, allowing them to calculate friction vectors and rotational forces in gears, pulley belts, and rotating machinery. Let us walk through the step-by-step mathematical proof of Theorem 10.1, which is a key proof for Class 10 students. The proof relies on a simple logical concept. The shortest distance from a point to a straight line is always the perpendicular distance. First, let our center be O, the point of contact be P, and the tangent line be XY. We choose any point Q on the tangent line XY, other than P, and join OQ. Since a tangent touches the circle at only 1 point, every other point on the tangent line must lie outside the circle. Therefore, the segment OQ must intersect the circle at some point R. Thus, the length OQ is equal to OR plus RQ, which is strictly greater than OR. Because OR equals OP, both being radii of the circle, we prove that OQ is strictly greater than OP. Since this is true for every point Q on XY, OP is the shortest distance, forcing OP to be perpendicular to XY. How many tangents can be drawn to a circle from a single point? It depends on the location of the point. If the point is inside the circle, no tangent can be drawn because any line will cross the circle as a secant. If the point is on the boundary, exactly 1 tangent can be drawn. However, if the point lies outside the circle, we can draw exactly 2 tangents. This leads to the second major theorem of the circle's syllabus, Theorem 10.2, which states, the lengths of tangents drawn from an external point to a circle are equal. This means that if we choose an external point P and draw tangents PQ and P are touching the circle at Q and R, the segments PQ and P are perfectly equal in length. Tracing the tangents on the screen, see how these 2 segments form a beautiful, symmetrical geometry. Let us prove Theorem 10.2, which is a beautiful demonstration of triangle congruence. Let our center be O, the external point be P, and the tangent contact points be Q and R. We join OQ, OR, and OP. This construction creates 2 right-angled triangles. triangle OQP and triangle ORP. Let us check their elements. First, radius OQ equals radius OR because they are radii of the same circle. Second, the segment OP is common to both triangles. Third, the angle OQP and angle ORP are both 90 degrees because a radius is perpendicular to the tangent at the point of contact. Therefore, by the right angle hypotenuse side, or RHS, congruence criterion, triangle OQP is perfectly congruent to triangle ORP. By corresponding parts of congruent triangles, or CPCT, this immediately proves that the tangent lengths PQ and P are equal. This triangle congruence proof unlocks several vital corollaries regarding angles. Because triangle OQP is congruent to triangle ORP, the corresponding angles are equal. This proves that the segment OP bisects the angle between the two tangents, meaning angle QPO equals angle RPO. It also proves that OP bisects the angle at the center, meaning angle QOP equals angle ROP. Furthermore, because the sum of angles in the quadrilateral OQP is 360 degrees, and the two angles at Q and R are 90 degrees, the remaining two angles, the angle between the tangents and the angle between the radii at the center, must add up to 180 degrees. This means they are supplementary. Surveyors and programmers use these angle relations to triangulate locations and program precise vector turns. Let us apply our tangents theorems to solve a classic concentric circles coordinate geometry problem. Concentric circles are two or more circles that share the exact same center point but have different radii. Imagine two concentric circles with radii 5 centimeters and 3 centimeters. We want to find the length of the chord of the larger circle which touches the smaller circle. Tracing the visual on your screen, let the chord be AB, touching the smaller circle at P. Because AB is a tangent to the inner circle at P, the radius OP is perpendicular to AB. In the right-angled triangle OPA, the hypotenuse OA is the outer radius, 5 centimeters, and the leg OP is the inner radius, 3 centimeters. Using the Pythagorean theorem, AP squared equals 5 squared minus 3 squared, which is 16, giving AP equals 4 centimeters. Since the perpendicular bisects the chord, AB is 2 times AP, or exactly 8 centimeters. Another beautiful application of Theorem 10.2 involves circumscribed quadrilaterals, which are four-sided shapes containing a circle that touches all four sides. Let a quadrilateral ABCD be circumscribed about a circle, touching its sides at points P, Q, R, and S. We want to prove that the sum of opposite sides are equal, meaning AB plus CD equals AD plus BC. The proof is incredibly elegant. We apply Theorem 10.2 to each of the four external vertices. From vertex A, tangent AP equals AS. From vertex B, BP equals BQ. From vertex C, CR equals CQ. From vertex D, DR equals DS. Adding all four equations together yields the sum. The quantity AP plus BP plus the quantity CR plus DR, which simplifies directly to AB plus CD. The right side simplifies to AD plus BC, completing the proof. This theorem structures structural weight distribution and stress analysis in load-bearing arches. Today, we have completed a beautiful geometric journey through the study of circles. We defined tangent lines and points of contact and proved Theorem 10.1 that the contact radius is perpendicular to the tangent. We mastered Theorem 10.2 using RHS congruence to prove that tangent lengths from an external point are equal and analyzed their supplementary angle relationships. Finally, we applied these theorems to solve concentric circles' chord lengths and circumscribed quadrilateral opposite sides. Tracing the circle's summary mandala, observe how tangent lines, radii right angles, and congruence proof spin in perfect mathematical harmony. These circular equations are the silent models running our technology, driving the focus of camera lenses, the rotation of engine crankshafts, the architecture of arches, and the graphics code in our digital games.